Okay, in this lecture, we will discuss various radar frequency, pulse radar, and continuous wave radar. So these are the commonly used frequency. So we can see, as we all know that these radar frequencies are in the range of gigahertz ranges, or it is in the range of microwave frequency ranges. Conventional radars generally have been operated at frequency extending from about 220 megahertz to 35 gigahertz. Then a skywave high frequency over the horizon radar might be at a frequency as low as 4 or sorry 5 megahertz, and ground wave high frequency radar as low as 2 megahertz. Then there is some codes in military application for the different band for different frequency bands like S, X, L, and etc. was employed to designate radar frequency bands. So these are the band designation and its corresponding nominal frequency ranges. So please go through this slide to get an overall idea regarding the frequency range corresponding to a particular band designation. Now we move on to the basic classification of radar. So the radar is classified as pulse radars, continuous wave radar, and MTI radar. Pulse radar utilizes pulse signals for transmitting, and continuous wave radar uses continuous wave signal. MTI radar is nothing but a pulse radar with a Doppler shift. So this continuous wave radar is usually used in low power, low range applications. Then MTI radar is used for detecting moving objects, where it considers pulse radar. I mean the pulse waves are used for transmission purposes. Now come to the block diagram of a pulse radar. So here the antenna is given. As in the last lecture I have mentioned, a common single antenna is used for transmission and reception purpose by making use of a duplexer. So this is a transmitter section. The first one is pulse modulator, then a transmitter, then the transmitter will transmit the signal to a target, and the returned signal is get back to the antenna and it is processed in this receiver section. Okay, so the first block is low noise RF amplifier, which will amplify the incoming signal. Then it mixes with a local oscillator. So the output of this is a intermediate frequency signal, which is amplified by a IF amplifier, which is usually a matched filter so as to get maximum signal to noise ratio. And there may be a detector. The detector is a demodulator. So usually for transmission section we will add some suitable modulation before transmission is like a FM, AM, pulse width modulations, etc. So that may be detected in this detector, and radar video amplifier is provided here, and after that a display is there to detect the object. You see the object, there may be a display which is usually cathode ray tube. Okay. So the purpose of the local oscillator and the mixer, this is the stage is to tune the incoming signal to a particular fixed frequency. So IF signal is a fixed frequency. The IF can be fixed according to the application. So IF is a fixed tuned frequency. So whatever be the input signal, we can tune the incoming signal to a particular frequency, so that the further processing will be easy. I mean, the if the free signal frequency is constant, the amplifier in the coming section will be designed according to a particular fixed rule. Otherwise, different amplifiers have to be used there. Then another important thing is when we mix the signal with a local oscillator signal. So the incoming signal might be at a gigahertz range, and after the mixing, the signal can be reduced to a low frequency signal. So the low frequency signal, the further processing will be easy. The low frequency signal can be detected very easily. For high frequency signal, again we have to use microwave components to the this particular section. So this is the main advantage of using this local oscillator mixer stage. The first one is we will be having a common tuned frequency. Then the second one is we can make the higher frequency a low frequency compared to the incoming frequency, so that the further processing will be easy. So these are the 2 points regarding this mixing. Then this mixing is known as super heterodyne. This is nothing but a super heterodyne receiver. Now, again, each and every sections are mentioned here. A pulse modulator, it produces a pulse modulated signal and it is applied to the transmitter. The transmitter, it transmits the pulse modulated signal, which is a train of repetitive pulses. Duplexer is here. It is a microwave switch which connects the antenna to both the transmitter section and the receiver section alternately. Low noise RF amplifier. This is the first stage in receiver section. It amplifies the weak RF signal which is received by the antenna. Then local oscillator, it produces a signal having stable frequency. The output of the local oscillator is connected to mixer. Mixer, we know that mixer can produce both the sum and the difference of the frequency that are applied to it, among which the difference of the frequency will be of intermediate frequency. ഞാൻ already പറഞ്ഞു നമ്മളിത് mix ചെയ്യുന്നത് we need to reduce the signal which is to be processed. അപ്പോൾ എപ്പോഴും ഡിഫറൻസ് സിഗ്നൽ മാത്രമേ അവർ പ്രിഫർ ചെയ്യത്തുള്ളൂ. Then IF amplifier have to be IF amplifier amplifies the intermediate frequency signal. Then there is a detector, it demodulate the signal. Video amplifier and a display. Generally it is a CRT screen. This is all about a basic pulse wave radar. Now, the Doppler effect. The Doppler effect is considered as the basic principle behind continuous wave radar. See, then firstly, what is Doppler effect? When there is a relative motion between the radar and the target, a feasible technique for separating the received signal from the transmitted signal is based on recognizing the change in the echo signal frequency caused by the Doppler effect. Okay, നമ്മൾ ഒരു particular ഫ്രീക്വൻസിയിലുള്ള സിഗ്നൽ ആയിരിക്കും ട്രാൻസ്മിറ്റ് ചെയ്യുന്നത്. ഇഫ് ദ സിഗ്നൽ ഈസ് മൂവിങ്, ഇഫ് ദ ടാർഗറ്റ് ഈസ് മൂവിങ്, റിസീവ് ചെയ്യുന്ന ഫ്രീക്വൻസി, സിഗ്നലിൻ്റെ ഫ്രീക്വൻസി ട്രാൻസ്മിറ്റ് ചെയ്യുന്ന ഫ്രീക്വൻസി ആയിരിക്കില്ല. ദർ ഈസ് സർട്ടൺ ഡിഫറൻസ് അക്കോർഡിംഗ് ടു ദ വെലോസിറ്റി ഓഫ് ദ ഒബ്ജെക്ട്. ദാറ്റ് ഈസ് ദ ബേസിക് പ്രിൻസിപ്പിൾ ബിഹൈൻഡ് ഡോപ്ലർ എഫക്ട്. Now, ഇതിനൊരു ഇക്വേഷൻ കണ്ടുപിടിക്കാൻ ഒരു പ്രൊസീജിയർ ഉണ്ട്. The Doppler shift in frequency is measured to find the velocity of the target. R is the distance from the radar to target. The total number of wavelength lambda contained in the two-way path between the radar and the target is 2r by lambda. See, 1 by lambda is wave number. I think all of you know about what is wave number, 1 by lambda. Then this is 2r by lambda. A particular range എത്ര wavelength included ആണ് 2r by lambda. So ഇത് ഇനി നമ്മൾ കൺവേർട്ട് ചെയ്തിട്ട് ഫേസിൽ റേഡിയനിൽ എക്സ്പ്രസ് ചെയ്യാനായിട്ട് we can multiply this with 2 pi. So each number of lambda is corresponding to 2 pi. So 2r by lambda is corresponding to 2r by lambda into 2 pi, which is equal to 4 pi r by lambda. This is equal to 5 phase. Okay. So if the target is in motion, the r is varying and the phase are also varying. Now what we are going to do is we will differentiate the phase with respect to time so that we will get the angular frequency omega d. The omega d equal to 2 pi into fd equal to d phi by dt equal to 4 pi by lambda into dr by dt equal to 4 pi Vr by lambda. So this dr by dt, change in distance by time, is velocity Vr by lambda, where Vr is the relative velocity of the target with respect to radar. Please remember, this is the relative velocity, not the original velocity of the object. This is the relative velocity of the target with respect to the radar. So by Now, by equating this two equation, this 2 pi fd is equal to 4 pi Vr by lambda, we will get an equation like this. Fd is equal to 2 Vr by lambda. We can replace this lambda in terms of f0 by c, where f0 is the transmitted frequency and c is the velocity of light and fd is the variation in the frequency. Okay. Now, um, so this is the simplest relation to correlate with the relative velocity Vr and the Doppler frequency shift. Now, this is another scenario where Vr, that is equal to V cos theta, where we considering, so considering the adjacent element, this V, adjacent element of V cos theta, which is moving towards the radar. So we can replace in VR 2 VR by lambda by VR with the 2 V cos theta. We will get the equation like this. Shift in FD. Then we can relate with the phase shift theta equal to 0. We will get maximum Doppler shift, and when theta equal to 90, we will get the